Assalamualaikum warahmatullahi wabarakatuh. My name is Noshawani binti Sunario with metric ID AW220001. So first of all, I will explain about the introduction for the evaporation process. Evaporation process is fundamental process in which solvent like liquid water is separated from the solution, yielding a product of high concentration or solid. The feed stream containing the solute and the solvent is fed to the evaporator. Then the evaporator is evaporate. It turns to the vapor, leaving the product of the interest. So energy balance is the process of keeping a record that is either input into a system or output from the system according to the first law of thermodynamics, to determine the heat and work exchange, as well as the change in internal, kinetic, and potential energies. Mass balance is also called material balance, and that one of the principle of chemical engineering, where according to the law of conversion of mass, the mass entering the system must be equal to the mass leaving the system. Degree of freedom, which is DOF analysis in process, refer to the number of independent variables that can be predetermined in a given system. This is done by comparing number of equations such as mass and energy balance with the number of unknowns, which are the flow rates, composition, temperature, and other else, to determine if a system is solvable under turning or overturning. Energy and mass balance are often used together in process calculation to determine the state and behavior of a chemical process. DOF analysis is used before solving mass and energy balance. A DOF analysis is performed to ensure that the system is solvable set of questions.
Okay, now I will talk about the mass balance. So for the mass balance, our question is to make a concentrated mango juice that is sweetened, and the unit squeeze juice has 15% of solid and needed to be raised to 30% solid through evaporation. And determine the degree of freedom for this question, and identify the volume of water needed to be evaporated given 300 of fresh juice. So from the question, we have to solve the degree of freedom and also identify the volume of water. And now I will talk about how to solve the degree of freedom. So first, our formula is a number of unknown minus the number of independent equation. So in this question, we have two unknown, which are the water evaporated and the product flow rate. And also, we have two independent equation, which are the solid balance and also water balance. After that, we substitute the value into the formula and we get the answer, which is the 0. And through this value, through this answer, we know that this system can be solved. Now, I will talk about the second problem in this question. So the second problem asks us to find the volume of water evaporated. And from the information that given, we know that A is equal to the 300, and the first is a 15% of solid, and this convert to the decimal place, which is 0.15, and 30% of solid also convert to decimal place, which also 0.30. And P is the product flow rate, and W, which we want to find the volume of evaporated water. So, uh, so first step is we need to have the overall material balance, which is the A equal to the P plus W. So A equal to 300, and then we substitute the 300 into this formula, and we get the first equation, which is the 300 equal to the P plus W. And then, and since we know that, according to the diagram that is the previous slide, we know that our type component is the solid. So that means we can use this information to solve to find the P. So uh, 0.15 A equal to 0.30 multiplied with p, and then we substitute a equal to 300, and then this equation left the one unknown, which is the p. And after we calculate, we find that the p is equal to 150. And after that, we use the p value to find the w, and then we substitute p value into the first equation. That is 300 equal to p plus w, and the p that we found is 150, so we substitute, and this equation left one unknown, which is the w that we want to found where we want to find. So w is also 150. So that means that the product flow rate is 150, which is equivalent to the amount of evaporated water. That's also 150. Okay.
So for the energy balance, the questions for this energy balance is as shown here. And beside the questions is the drawing of the questions, the evaporator, and the informations from the questions have been put in the drawing. And the calculation start with OMB, overall material balance. So OMB is F equal to L plus V, whereby F is 7,000 kg per hour, the V, and L plus V. L is the concentrated product, and V is a vapor. So this is the first equation. And in this questions, we have the components balance, which is the type components is the solid. So solid SFF equal to XLL. So 0.02 from 2% solid times with 7,000 is a V equal to 0.04. The 4% solid times with L, because we want to find L. So the L value we got is 3,500 kilogram per hour, and then we substitute the L value in the first equation, and then we got the V value is the same as L, which is the value of V is 3,500 kilogram per hour. So next calculations is temperature of V, TF. We got 353 Kelvin from the questions. So we change it to Celsius. We got 80 degrees Celsius, 80 degrees Celsius for the temperature of V, TF. So we take a look at the steam table at the temperature of 80 degrees Celsius, enthalpy of heat. We got HF is equal to 335.02 kilojoule per kilogram. And if the evaporator at atmospheric pressure, the boiling point of water at 101.4 kilopascal. So the boiling point of water Tb equal to 373 Kelvin. So we change to the Celsius, we got 100 degrees Celsius for the boiling point of water. And then from the steam table at the temperature of 100 degrees Celsius, we find Hb equal to 2,675.6 kilojoule per kilogram, and in the HL we got 419.17 kilojoule per kilogram. And also from the steam table, we find enthalpy of the liquid condensate at 143.3 kilopascal. We got Hs equal to 461.4 kilojoule per kilogram. And next from steam table, at enthalpy of steam 143.4 kilopascal, Hs value is equal to 2691.1 kilojoule per kilogram. And the saturation temperature Ts is 383 kilogram, 383 Kelvin. So we change Kelvin to Celsius, we got 110 degrees Celsius. So for the energy balance equation, FHL plus S in the bracket HS minus HS equal to LHL plus VHV. So to find S, we substitute the value that we obtained before in the previous calculation. So we got S value equal to 3,806.14 kilogram per hour. Next, we find the heat of the system QS. So QS equal to S times with HS minus HS equal to S lambda. So we substitute the S value, and then HS and HS value to 2691.1 minus 461.4. We got the value of QS equal to 84 at 6550 minus 84 at 6550.358 kilojoule per hour. And then we convert to watt, we got Qs equal to 2357375.10 watt. And you want to find the overall heat coefficient U, we substitute the value in the equations. Q equal to U A delta T equal to UA times with in the bracket Ts minus Tb, and then we substitute the value Q equal to 3357375.10, and then we substitute the A value area 70, and then we minus the temperature difference 383 Kelvin minus with 373 Kelvin, and then we obtain the U value equal to 3367.68 value watt over meter square Kelvin.
Evaporation calculations are used to concentrate mango juice from 15% solids to 30% solids, requiring a detailed material balance. The process is considered steady state, continuous, and open with input flow rate of 300 kg per hour of fresh juice. The system is time invariant, simplifying calculations and providing a balanced system over time. To solve the problem, the degrees of freedom DOF are determined and two independent equations are identified: product flow rate P and the amount of water evaporated W. Continuous processes with high efficiency and consistency in returning concentrated juice can be important for industrial and large scale production criteria. As an open system, the evaporator removes and discharges mass across system boundaries, ensuring a constant mass entering and leaving the system. The total mass balance equation and solid balance equation are used to find product flow rate and water evaporated. Quality controls are implemented to ensure product consistency and avoid interference with the juice flavor and nutritional value. The process efficiency of evaporation in concentrating mango juice is confirmed, demonstrating the importance of a steady state continuous open system for large scale production efficiency.
The system is in a steady state as it is a continuous operation where the continuous flow is 7,000 kg per hour, is in a constant condition where the feed rate, concentration, and temperature is constant. It is an open system as there was a continuous input and output of mass, which were the solution feed and the evaporated liquid. The feed temperature was 353 Kelvin and the boiling point at the atmospheric pressure of 101.4 kilopascal was 373 Kelvin. So using the steam tables, the enthalpy of the feed, HF, is 335.02 kilojoule per kilogram, while the enthalpy of the vaporization, HV, at the boiling point was 2675.6 kilojoule per kilogram. So the enthalpy of the heating system, HS, at 143.4 kilopascal was 2691.1 kilojoule per kilogram. In the condensate enthalpy HS of 461.4 kilojoule per kilogram. So the energy balance equation for this equation is FHF plus S in bracket HS minus HS equal to LHL plus VHV. When substitute the known values, the steam flow rate S was determined. As calculated, the value of S is 3806.14 kg per hour. So the heat transfer rate QS was calculated using the steam flow rate and the latent heat of vaporization. So the result was QS is equals to 8,486,550.358 kilojoule per H, and converted to watts is 2,357,375.1 watt. Using the equation Q equals to U A delta T, where the U is the overall heat transfer coefficient, A is the heat transfer area, and delta T is the temperature difference between the steam and the boiling liquid in order to calculate U. So the area is given as 70 meters square and the temperature difference is 10 Kelvin. The overall heat transfer coefficient was found to be U equals to 3,367.68 watt per meter square Kelvin.
The DOF analysis is used to calculate mass and energy in the evaporation process by identifying unknowns and solving independent equations. For example, fresh juice with a 15% solids concentration as a mass of 45 kilogram per hour, while concentrated juice as a mass flow rate of 150 kilogram per hour. The unknowns are W, which is water evaporated, and P, product flow rate. Independent equations for total mass balance, solid balance, and water balance are used to solve the equations. The total mass balance equation A is equals to P plus W relates the fresh juice flow rate to the sum of concentrated juice and evaporated water flow rates. The independent solid balance equation, which is A times 0.15 is equals to P times 0.30, gives a mass balance for solids in both juices. The independent water balance equation A times 0.85 is equals to P times 0.70 plus W describes how the water comes out in streams. Since there are two unknowns and two independent equations, then DOF is 0. That means it is exactly specified. Solution of the equations yields the product flow rate P 150 kilogram per hour and water evaporated as 150 kilogram per hour. The DOF analysis determines variables subject to mass and energy balances without relying on other information. The conclusion of the report on mass and energy balance of evaporation process emphasizes the effectiveness and efficiency of the evaporation process in concentrating solutions such as mango juice. The detailed mass and energy balance calculations demonstrate the ability to achieve desired concentrations while maintaining system stability and predictability. The report underscores the importance of continuous, steady state operations for large scale production and highlights the role of a proper system design in achieving high quality output. Overall, the study illustrates the critical aspects of mass and energy balance in optimizing evaporation processes for industrial applications.
So there are a few recommendations that can be implemented. First is to evaluate and improve the heat source for the evaporation. So this can encompass the incorporation of waste heat recovery devices or analyzing the feasibility of utilizing renewable energy in the establishment. So the second is by improving the thermal conductivity, which is also another significant concern. So this can be done by proper care and cleaning of the heat exchange surfaces in order to minimize scales and fouling effects on the heat transfer coefficient. Third is consistent management and monitoring of process factors including temperature, pressure, flow, and concentration. So automating the control system in this area makes it possible for the taking of adjustments of this area should there be a provision from time to time to achieve an optimal vaporization condition and product quality. And lastly is proactive maintenance practices which were critical for sustaining efficient operation. Establishing regular inspection and cleaning schedules, along with promptly replacing worn out components, helps prevent unexpected downtime and ensures the longevity of the equipment.